Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, everybody. Welcome to Lecture 3.4, and this will cover how to use MEEP in a lot more detail. So let me just give you an overview of the ways in which you can interact with MEEP. There are actually a few different interfaces, and so the reason why we have these is that historically, MEEP was kind of developed with a C++ type interface. And it's a very nice interface, but it's not as widely used now as the scheme interface. Because the scheme interface was designed to make easy problems easy to implement, whereas the C interface was more kind of targeted towards power users, basically active researchers in finite-difference time domain. And then there's actually a third interface, which has now become available through nanoHUB, which is essentially a graphical user interface. And that's actually a very nice interface, and there's actually a branch off of the main MEEP tool called MEEP PV, which is specifically targeted to help people solve PV-related problems. And then I'll be going through that in the following series of lectures after 3.5. So in any case, just to give you a little more detail about each interface, the C++ interface, the way it works basically is you write code in C++, and then there's a specific MEEP library, and that library will actually call certain functions or create certain functions that wouldn't otherwise be available to a C or C++ user. And as you can imagine, because it's in C, it's a very powerful, very flexible interface, and it's also very fast. The downside, of course, is that you have to A, be good at programming in C or C++, and then B, you have to compile it every time you want to make any changes. The scheme interface actually overcomes some of those difficulties because it's a scripted language, so no compiling is necessary. It basically uses the scheme interpreter, and then the scheme interpreter is augmented by this library called libctl, which was developed by Stephen Johnson to kind of supplement the base capabilities of scheme and Guile. In particular, to make simple problems easy to implement, but also still help you solve hard problems. And probably a little easier to write than the C++ interface, but the catch is maybe not quite as flexible or powerful. So there can be some problems that you may have to switch to the C++ interface, but actually most of the examples that I'll be giving would be either in Scheme or the nanoHUB GUI. And like I said, we'll talk about that after lecture 3.5. So as far as like kind of the structure internally of MEEP's code, I think there are a few key concepts that are really crucial to understand like kind of the way that MEEP works. So first of all, it really cares about having some sort of computational cell size, because that's kind of the fundamental determinant of the difficulty, computational difficulty of the problem. So it effectively is determining kind of in MEEP units how big is the computational cell and whether it's 1D, 2D, or 3D. And so then specifying the corresponding number of dimensions. And of course, the system can either be periodic in certain directions, or it can be terminated and be essentially semi-infinite with no reflections, which would be a perfectly matched layer. And you can also have mixed boundary conditions where you kind of have a little bit of each, depending on which face of the structure. And usually these are Cartesian, but sometimes you can also have cylindrical coordinates, and you can have 2D as well as 3D. Now, another thing that's very important is materials in MEEP. And of course, like you're probably very familiar with kind of material that has a fixed dielectric constant, like say glass, which would have an index around 1.46, or epsilon of 1.46 squared. But then, of course, there are more complicated types of objects, but a lot of these can be captured as what we call the medium type interface. A second type of material that could be important for some calculations is the so-called perfect metal, which is essentially a perfect reflector. It could be thought of as kind of the idealization of what would happen if you had a metal which had no ohmic losses. And then third, there's actually this so-called material function where the material would actually vary in terms of the refractive index as a function of position. And so then this can give you like a very general sort of material, including all kinds of unusual structures like holosteric elastomers, for example, just to take one example, which is basically a material that's both anisotropic and has a rotating axis of anisotropy as a function of position. Now, as you can imagine, another thing that's very important are all the geometric objects, which are essentially the building blocks of any kind of real geometric structure composed of different dielectric materials. And certain key types that are widely used include blocks, which could be either cubes or something that's distorted from a cube, a cylinder, so usually a right cylinder, and then a cone, kind of along similar lines, which kind of comes up to a point, and then spheres, and then distortions of spheres like ellipsoids. So those are all allowed within MEEP. Of course, you could create something more general as well. And then another key concept is symmetry. The reason we care about symmetry is that it allows us to simplify the problem both computationally and from an analytic perspective. And we can basically implement three types of symmetry: mirror symmetries, twofold rotational, and then fourfold rotational symmetries. And so those are all kind of well defined, and those help cut down on our computation time quite significantly. And then the PML, which we talked about earlier, that's the perfectly matched layer that prevents any reflection, so it acts like kind of a semi-infinite region. And then you can modify both the thickness and the direction of PML so that PML is only on certain faces of your computational region. Another key type is the source. And so there are three types of sources that are used. First of all, the Gaussian source, that's the most common choice, in which you basically would choose a source that would be Gaussian both in time and frequency domain. And of course, it's a well-known property that if you take the Fourier transform of a Gaussian function, you get another Gaussian function. So that's like why it's widely used. And this allows us to use like what would be a relatively fast pulse to excite a broad range of frequencies in a well-defined fashion, and thus look at kind of an entire frequency spectrum all in one simulation. The second type is the continuous source, which basically acts like a continuous wave laser or something. And then finally, there's a custom source in which you would have a custom specified time dependence of the source, right? And so that's in case the Gaussian or continuous source doesn't work for you. Another thing that's very important that kind of goes hand in hand with the source is the flux region. The reason why we are so interested in using flux regions is that in order to calculate like a reflection or transmission spectrum, then we have to look at the Poynting flux through various planes that would be interposed between the source and then some sort of either filter or other dielectric object that we're trying to study. And the Poynting vector is essentially given as E star cross H, and that basically tells you the amount of power that's flowing per unit area in like at least the real part is the real power flow. And then if you integrate that over a certain area, then that gives you the total power flow. And so you can calculate a frequency spectrum with that information. If you both Fourier transform the E fields and the H fields before you do the integration. And then usually the key thing is to just specify essentially like where the flux region is and its weighting compared to the other flux regions, so you can accurately calculate the total amount of power that's going in and out. And it's also well known that if you calculate flux through a enclosed region in space, then that also has to equal the total amount of energy that's either being added to or subtracted from a system through absorption. And so basically, that is basically a rewriting of the energy conservation condition and using Stokes' theorem to basically transform a volume integral into a surface integral. And from a computational perspective, it's much more advantageous to use a surface integral because the amount of time that it takes, especially for a large volume, is going to be much smaller. So that's why we do that. Now, as far as other functions go, so these are kind of like more unique to MEEP in some sense. There are a few things that are all called run functions. And then basically what's nice about run functions is they allow you to kind of converge over time to the correct answer and basically accurately gauge how much time your time domain simulation needs to run for in order to get the right result. And so the simplest approach is basically to give it a certain number of time steps that it needs to run for until you feel that it'll be completed. There's also run sources in which it just runs until the source has turned off. Of course, if the source never turns off, that doesn't really work. So it's better for Gaussian sources. And then there's also run sources plus, which would say run for the time that the source is run until plus like a specified fixed amount of time, like in run until. So it's basically combining the first two into a single command. Stop when fields decayed is a very nice function because that basically would say that you would run the simulation until all the fields inside of the structure that we're studying would have gone away to a certain level of accuracy, say like there's no more than 10 parts per million left of the original peak amplitude or intensity of your energy coming in, right? So then that would give you a certain level of confidence in the resulting frequency spectrum that you calculate. And then there's also this so-called run k-point command. And then this is very useful if you're trying to calculate, for example, a band structure in your dielectric region, and you want to use different key points or different boundary conditions, essentially in the periodic directions. So the step functions include the following. So there's one in which you would output the epsilon of the structure that you just created. So this is a very good way to check that your geometry is created properly. There's one in which you would output various field components like E field Z or B field X and so on. And then you can also output the total power, and you can even generate a PNG file or image file directly from the raw data within MEEP, which is a very nice feature. So let me give you a specific example of like what can be done here. So what you see is essentially index-guided waveguide in which you would basically, first of all, create the lattice itself. So you see on this first line, you create the lattice, and then you would basically create the block. And then this block is essentially your waveguide itself. And it has a dielectric constant of 12. You can see here, epsilon of 12. And the size is only limited in one direction because we already created a 2D structure and we want it to be essentially infinitely long in the x direction. And so then that's why we make it infinity, 1, infinity. The reason infinity is a safer choice in the no size direction is because if we did subsequently add something in the no size direction, it still would fill all the space. And then you see here, basically we set up a source, which is going to be a CW source at frequency of 0.15, which is centered at -7,0. So this is kind of on one end of the lattice. And because the lattice is of size 16, -7 corresponds to one MEEP unit or 1A away from the very end because it goes from -8 to 8 in the x direction and then -4 to 4 in the y direction. And then you see here, we calculate or add a PML layer, which kind of goes right up to that edge of where the source is located. we set the resolution to be 10, which means that for every A, there are 10 lattice points. And so then that means 160 in the X direction and then 80 in the Y direction. Of course, only 1 in the Z direction. And then we run until 200, which means run for 200 time steps in MEEP units, which are units of A over C. And then we output the epsilon at the very beginning, and then we output the E field in the Z direction at the end. Okay. And so this is just showing like kind of the output of the epsilon. And so you can see that it looks like a long, thin dielectric. Of course, it's bounded by the size of the lattice itself. But if you made the lattice longer, it'd be longer because it's specified to be infinitely long. And then you see that the source basically creates like an EZ field, and then that EZ field starts to propagate down the structure. And it alternates like positive and negative E. And of course, if you looked at the B field, you'd see something similar but orthogonal going down this waveguide, right? So that makes sense. So then what happens if we put a bend in the dielectric structure? So if you've already studied these kind of problems before, like for index-guided waveguides, you know for a fact that if the bend radius is too small, then you tend to have light leak out. And that's because you break the condition for total internal reflection, which is that the angle at which the light would hit the edge of the waveguide, the high index waveguide, would be greater than some sort of critical angle, okay? But if you basically are creating a very sharp turn, then that means that you're hitting it almost like kind of normal to that interface, and so you tend to escape very easily. So from a ray optics perspective, it's very easy to predict that this is going to have some losses. But nonetheless, we're going to try to basically create a structure that looks like this. And you see here, of course, we had to expand the size in the X direction as a result, or sorry, in the Y direction, I mean, as a result, so that we have enough room for this to really fully bend. And then we create a block, not only one that goes up to here, but it doesn't go all the way to the end anymore, but it's only 3/4 of the size of the X direction. And then we create another block that's here, that's kind of aligned so that they will coincide right at this corner. And then we use the same resolution as before. And of course, we need to set up a PML layer. So you'll notice in this case, since we make PML thickness of 1, this is basically by default going to cover all of the regions that we're simulating in X and Y directions with PML. And if we compare that to what we had before, you can see that it's pretty much the same. Now, when we make the source now has a slightly different wavelength just for the sake of exploring different wavelength propagation. And you can see the position is kind of like in one corner, and it's not extremely big. And it basically is going to create a whole movie of like the propagation. Okay, so what you can see is like as it starts to run, then you can see that the light is kind of showing up at this corner, like where the source is, but then the light is actually propagating down the waveguide, but then it's radiating out here at this short, sharp corner. Some of it is getting down here, but you can see that the fraction is very low. And so now I'm going to show the movie again. And so what I'd like you to look for is you can see this initial propagation of the waveguide. So this is exactly what would happen for a completely straight waveguide, almost exactly the same. But it's just when most of the light gets here, then it starts to have a problem, and it's much more likely to get radiated outwards than to propagate down. Okay, so that kind of illustrates the drawback of traditional index-guided waveguides for very tight spaces. Now, if we wanted to kind of quantify exactly how bad is this, like we don't really know. All we know is that it looks like you lost a lot of power. But how much did you really lose, and how much does that depend on the frequency, right? We don't necessarily know right away. Of course, we could do an analytical calculation, but it'd be very hard to really get an exact result. So instead, what we're going to try to do is we'll set up a like first of all, like the blocks like we had before, but we'll also create like flux planes to kind of keep close track of how much light is going in and out. And although I'm going through this kind of fast, what you can see here is basically we pick 100 frequencies that we're going to look at both the transmission and reflection by setting 2 flux planes at the beginning and end. And then we're going to basically make an overall number of flux regions that's equal to 2. And so you can see here, basically, we're creating like flux regions in different positions depending on whether the structure has the bend or not. Okay, because like what we're going to try to do is quantify how much did we lose just from the bend. So if we propagated straight and then we propagated around a corner, like how much extra loss is happening as a result of having that corner. Okay, and so then that's why we only pick one or the other in each given simulation for the transmission, but we can always put the reflected flux in the same position either way. Okay, and so then this kind of shows the results. So you can see here that the overall reflection is actually kind of reaching a peak right at this frequency of 0.15, and it's actually very strong at this position, like over 60% for this bend. And then you can see that as a result, the transmission drops very poorly to below 20%. Okay, so now you're losing a ton of that power. And so you can see that the overall power loss becomes like very substantial. So in particular, you could argue that the loss is up to like 60–65% at that frequency, and then even away from that frequency, it's at least 30%. So in the next class, we're going to discuss some further examples using MEEP, getting more into nonlinearities.